Chapter 1, Part 4, Exceptions to the Octet Rule and Formal Charge. So let's start with exceptions to the octet rule. The first thing that I want to say about this is that this is not overly common in organic chemistry. There's one exception to the octet rule that you'll see regularly, and that is a carbon that only has 6 electrons around it and a positive charge. It's called a carbocation. You will see that all the time. But outside of that, you don't really see a lot of exceptions to the octet rule in organic chemistry. So this is more just reminding you about this than actually, emphasizing it as a super important topic. So second period elements are restricted to the octet rule because they only have the 2s and the 3 2p orbitals for bonding. Remember, period refers to a row in the periodic table. So we're talking about the second row and up are restricted to the octet rule. But once you introduce the d orbitals, the 3 d orbitals, you can start using those for bonding as well, and that means that you have some exceptions to the octet rule possible. So our examples are going to be sulfuric acid, phosphorus pentachloride, and sulfur hexafluoride. Notice none of these contain carbon. So let's talk about sulfuric acid first. Let's go ahead and just work through this one together, and then you can work on the others on your own. So let's add up all of our valence electrons. We're just going to follow the same format that we have been for our Lewis structures. So we have one sulfur atom. Sulfur comes with 6 electrons. It is directly below oxygen in the periodic table, so it's going to have the same number of valence electrons. We have 2 hydrogen atoms. Not sure why I skipped those. I just got excited about sulfur, I guess. They each have 1 valence electron. So that gives us 2 to use from hydrogens. And then we have 4 oxygen atoms. Nice big space between those. And each oxygen atom comes with 6 valence electrons. So 4 times 6 is 24. So that's a lot of electrons, right? We haven't really done one that has this many before. That's 32 valence electrons to use. Okay, so let's think about this. We don't have carbon to automatically assign as our central atom. So another kind of fun rule that you can use, or not really a rule, but more of a trend, is that if you only have one of something in your formula, it's likely to be the central atom or one of the central atoms. If you have multiple of something, such as the oxygens here, it's probably not the central atom. So let's assign sulfur as our central atom. And then let's just try and put everything else around sulfur. Let's start with putting the oxygens around there on single bonds. So that already gives sulfur a full octet. In order to give the oxygens full octets, we could do 3 lone pairs each. But that doesn't use the hydrogens. We have to put the hydrogens on here somewhere. So let's erase some of these. Throw the hydrogens on. And remember, the hydrogens don't care about having a full octet, so they are not a problem. Another option that you might come up with if you're also kind of working this out on your own is something like this, because we already said that we have some exceptions to the octet rule. Now I'm going to go ahead and tell you this is not correct. Let's talk about why. This is going to use, we have 8 valence electrons here, 10, 18, 26, 28, plus 8 more. That is 36 valence electrons. That's not going to happen. We only have 32. So we're going to go ahead and erase this guy. Now regretting drawing out all of those electrons. Okay. So this is why the original one that I drew is preferable. Now let's look at this and count up all of our electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So that uses the correct number of valence electrons. That's really good. So this actually is a valid Lewis structure. Now, in order to draw it this way, we'd have to add in formal charges, which I know we haven't covered yet. That's coming up at the end of this video. It's a little out of order with regards to that. But we're going to end up having to put a charge of -1 on each oxygen and a charge of +2 on the sulfur. Now, there's a way that we can remedy that. If we draw the structure a little differently with double bonds to each of those 2 oxygens, and 2 lone pairs on each oxygen. This uses the correct number of valence electrons as well. You can count them yourself. But what it does is it gives sulfur way too many electrons around it, right? Sulfur has 6 bonds to it. That's going to be 12 valence electrons. And this is our exception to the octet rule. So sulfur is currently breaking the octet rule and doing it gleefully because there are no charges on this molecule. And we're going to learn a little later in this chapter that if you have an option between a structure that has multiple formal charges, even though overall this molecule is neutral, or one that is entirely neutral on every atom and shows no charges, that the one with no charges is going to be preferable. So this is the generally accepted structure of sulfuric acid. Okay, phosphorus pentachloride and sulfur hexafluoride. You can do these on your own. I'll go ahead and draw out the correct structure for you. Okay, these are the correct structures for these 2 molecules. Phosphorus pentachloride should have 40 electrons around it. 40 valence electrons, and sulfur hexafluoride is going to have 48 valence electrons. That's a lot. So the only way to do this is actually to arrange the halogens around those central atoms and give the halogens full octets. This gives phosphorus 10 valence electrons around it, which breaks the octet rule, and it gives sulfur 12 valence electrons around it. But this is the only way that you can do these molecules. Also, you may have been tempted to do something that you might have seen in Gen Chem, where instead of drawing out the pairs of electrons individually, you draw them as lines. This is totally acceptable in drawing a Lewis structure, but it's not ideal in organic chemistry because organic chemistry does a lot of reaction mechanisms, where we actually show how electrons move in order to accomplish a reaction. And in order to do that, it's better to get in the habit of drawing the pairs of electrons out individually. So I encourage that more than the lines because the lines don't really work in a reaction mechanism. Okay, let's talk about formal charges. Formal charges are actually very easy to calculate. Once you get really familiar with the periodic table and you've worked a lot of them, it'll actually come to you pretty quickly without even having to do a calculation. But in order to calculate it, you have to first ask yourself how many valence electrons should an atom have? When you look at that atom on the periodic table, how many valence electrons does the periodic table say it comes with? How many electrons does it actually have in the molecule? The difference between those 2 numbers is the formal charge. So we have 2 examples to look at here. The first is ammonium. Go ahead and pause for a second and draw out the structure of ammonium yourself. Okay, the structure you should have come up with is nitrogen with 4 hydrogens around it. And overall, this molecule has a positive charge. Now the question is, where on this molecule does the positive charge live? And in order to answer that, we have to ask ourselves these 2 questions. So the hydrogens are not usually where the formal charge is, so let's go ahead and disregard them. The nitrogen is currently experiencing a full octet. which is great. Nitrogen comes with 5 valence electrons. If you look at the periodic table, it's in the 5th group, so it has 5 valence electrons. Now, how many of the 8 electrons around it does nitrogen actually own? The answer is half. So it gets 1 electron per bond. So another way of asking this question is how many bonds? And you also want to add up lone pairs. But nothing in this molecule has lone pairs, so we don't have to think about that right now. So nitrogen has 4 bonds, which means it owns 4 of the electrons around it. So we're going to subtract those, and that gives us +1. The +1 charge is on the nitrogen atom because it is currently missing 1 of its electrons. Now let's look at the acetate molecule, which is our other example. The structure of acetate has the 2 carbons linked together. All of the hydrogens are actually on 1 carbon atom. We have a double bond to an oxygen and a single bond to the other. And we're going to have some lone pairs. Ooh, I just drew a positive charge randomly. This molecule has a negative charge overall. The question is, where does the negative charge live? So let's look at these. Let's not worry about the hydrogen atoms. Let's look at carbon. Carbon is supposed to come with 4 valence electrons. Let's call this carbon A, we'll call this carbon B, oxygen A, and oxygen B. So carbon A, it's supposed to come with 4 valence electrons, and in this structure it has 4 bonds, so that's 1, 2, 3, 4 electrons that it owns. That is a difference of 0, so the charge is not on carbon A. Let's look at carbon B. Carbon B has 1, 2, 3, 4 bonds around it. Two of those bonds are tied up in a double bond, but there are 2 electrons in each of those bonds, and carbon owns half of them. So that's 4 minus 4, which equals 0. So it's not carbon B either. Oxygen A. Oxygen should come with 6 valence electrons. Oxygen has 2 bonds, so it owns half of those bonds. That's 2 electrons. So 2, 4, 6, because it also owns the lone pairs. So it's not oxygen A either. Okay, let's look at oxygen B. Oxygen B has 1 bond, and it gets 1 electron from that bond. And then it has 2, 4, 6 from lone pairs. So it should have 6, but it currently has 7 around it. That's a difference of -1. So oxygen B has a negative charge. Now this is a full how-to on formal charges, which we just did. So I'm just going to put these steps up here, and this is a way to work through this yourself if you need a little more of a reminder when you're doing practice problems. There are also some equations that you can use. There are 3 different versions of this equation, and they all say the same thing, but one of them is much easier to use than the others, and that's the top one. A lot of people use this one, where you add up the number of bonds and the number of non-bonding electrons, which is actually what we were doing on the previous page. But the issue with this is that sometimes people forget that you have to add these numbers up first and then subtract them. Because if you ignore the parentheses and you subtract the number of bonds and add the number of non-bonding electrons, let's look at that oxygen B that we just had. All right, ignore the rest of the molecule. We're just talking about oxygen B. Oxygen B is supposed to come with 6 valence electrons. We subtract the number of bonds and we add the non-bonding electrons. That would be 6. That would give us 11. So if you did it this way and you forgot about the parenthesis, you could give yourself a +11 charge on oxygen. That's really, really wrong. That's not the right answer at all. And unfortunately, I see students do that really, really often. So I would encourage you not to use this one because as you use it, you might forget about the parentheses. The easiest one to use by far, if you're going to use a formula, is the top one. So let's look at that carbon oxygen situation one more time. This was oxygen B from acetate on the previous page. Oxygen should have 6 valence electrons. We subtract the number of bonds and we subtract the number of non-bonding electrons. This gives us -1. If you use the second one, sometimes students get confused by this phrase. So I support the first one. Whichever one works for you is the correct one for you. So let's do some practice problems. Go ahead and pause for a second and try and work these out yourself. Figure out which atom has the charge on it and what that charge is. Okay, let's work these out together. In order to save time on the video, I'm going to do something that hopefully you already kind of figured out for yourself, and we're only going to look at the relevant atom. I also want to point out that I did something kind of mean, and I left off all the lone pairs on the fluorines. There are no other lone pairs in these structures, but I was hoping that you'd recognize that halogens come with lone pairs. So let's look at the first structure. This is the pyridinium ion. It has a charge of +1. Now, if you did all of the carbons, you would find that all the carbons have 4 bonds and no lone pairs. So all of the carbons are neutral, and so are the hydrogens. It's the nitrogen that's weird. So the nitrogen is supposed to come with 5 valence electrons, and it has 1, 2, 3, 4 bonds to it and no lone pairs. This is +1. So the positive charge on the pyridinium ion is on nitrogen. In the next molecule, your only options are carbons. So as you worked through these, you probably noticed this carbon has 4 bonds, so does this one, this one, this one, and this one. The carbon that I didn't circle is your standout, and this is a carbocation. This is something that I briefly mentioned earlier. And this is going to be a positively charged species, as the word cation implies. So let's figure out where that comes from. So carbon is supposed to come with 4 valence electrons. This carbon has 3 bonds around it and no lone pairs. This is a +1 charge. Okay, our last one is boron tetrafluoride. So we have 4 fluorines around boron, and boron is kind of a weird species, but it's supposed to come with 3 valence electrons, and it currently has a full octet, which means it has 4 electrons around it. That gives us a -1 charge on boron. So those are the correct charges that you should have come up with for these molecules. I want to mention also real fast that we looked at a weird structure of sulfuric acid earlier, and I don't think I drew this structure back out in this PowerPoint, so I want to draw it out again and look at the formal charges that we assigned, or that I assigned rapidly and said we would talk about later. So we have 2 weird oxygens and a sulfur. So the oxygens are equivalent to each other the way that they're drawn. They each have a single bond and 6 lone pairs. Remember, the oxygen is supposed to come with 6 valence electrons, but each of these has 1 bond and 6 lone pairs. That equals -1. So each of the oxygens have a -1 charge. And then the sulfur in the middle, I gave a +2 charge to earlier. Let's look at where that comes from. Sulfur comes with 6 valence electrons. It has 4 bonds around it. It has no lone pairs. That equals +2. So the sulfur in the middle has a +2 charge. Okay, the last page on this is a bonding rules table. These are trends that you're going to notice the more and more Lewis structures you draw out and the more formal charges you calculate. But if you're a good memorizer, this is a good way to kick off your Lewis structure drawing. It'll help you draw the structures much more quickly because you'll know what each atom prefers. So let's start with carbon. Carbon is the star of organic chemistry. Carbon has 4 valence electrons. When carbon is neutral, it has 4 bonds. There are some special charged species, which is a carbocation. Carbocations have 3 bonds. They do not have lone pairs. This creates a +1 charge on carbon. There are also carbanions. There are a couple different ways to do this, so I didn't put this on here. The times that you'll see it in OCHEM, you're going to make the carbanion. You'll know exactly where it came from and why it has a -1 charge or -2, whatever you've done to it. The next element is nitrogen. Nitrogen comes with 5 valence electrons. When nitrogen is neutral, it has 3 bonds and 1 lone pair. And I want to remind you that 3 bonds can mean 1 single bond and a double bond, or it can mean 1 triple bond. But it just has to be 3 bonds in some way and 1 lone pair. That's how nitrogen can be neutral. Nitrogen has charged species as well. And remember, these are your special circumstances. These are not your normal Lewis structures. So this is not where I would start if I was drawing a Lewis structure. If nitrogen has 4 bonds, it will have 0 lone pairs. That gives it a positive charge on nitrogen. You can also have 2 bonds and 2 lone pairs. This will give a negative charge on nitrogen. Oxygen comes with 6 valence electrons. It likes to have 2 bonds and 2 lone pairs. You can also have 1 bond and 3 lone pairs. This is a species that we've seen multiple times in this slideshow. That'll give a negative charge on oxygen. If you have 3 bonds and 1 lone pair, which is pretty rare, you don't see this a lot, this is an oxonium ion, it's going to put a positive charge on oxygen. You really only see this if you've protonated something. So a good example is the hydronium ion. Hydrogen has 1 valence electron. It likes to make 1 bond, and we don't do anything crazy with nitrogen. Halogens come with 7 valence electrons. They like to make 1 bond, and they will have 3 lone pairs on them. We don't really do anything special with halogens in organic chemistry, and I want to emphasize that these rules are specific to organic chemistry. If you look at like chloric acid or bromic acid, I'm not talking about hydrochloric and hydrobromic, which are simple, hydrochloric, hydrobromic. I'm talking about chloric, bromic, iodic. These acids all have many bonds to the halogens, and those are going to be some special species. We're not going to use those in OCHEM really. You're only going to see halogens when they're attached to carbons. Boron comes with 3 valence electrons. When it's neutral, it has 3 bonds, no lone pairs. This is not a full octet. This is only 6 valence electrons around boron, and it's actually okay with that. Boron can also have 4 bonds, which would give it a -1 charge. So again, if you can memorize this, you're going to get through your Lewis structures very, very quickly. Something else that I want to point out is that the number of valence electrons can give you a pretty good shortcut to the number of bonds, because the number of valence electrons that it comes with and the number of bonds that it can make should equal 8. So nitrogen comes with 5 valence electrons. It wants an octet, so it's going to make 3 bonds, so it can gain 3 more electrons. Oxygen comes with 6 valence electrons. It needs 2 more, so it's going to make 2 bonds to get there. And then hydrogen, again, doesn't care about the octet rule, so ignore hydrogen. Halogens come with 7 valence electrons, and in order to get an octet, it's going to make 1 bond. And now the number of lone pairs doesn't, participate in this right here, but what it does is completes the octet around that species. So if you have carbon bonded to a halogen, in order to make carbon happy, let's give it 3 hydrogens. The halogen has 1 bond. All the rest of its valence electrons have to be lone pairs, and that gives it its octet. So this is a good way to recognize how quickly you can draw these structures. Boron, you're not going to see super often in OCHEM, so I would focus on the top part of this chart.